All right, today on The Explainer, we are diving into a really revolutionary and honestly kind of mind-bending new idea. It sits right at the crossroads of AI and quantum mechanics. We're talking about a concept that could completely change how our AI systems understand language, making them smarter, faster, and just unbelievably more efficient.
So, to really get why this is such a big deal, let's just start with a number. A really big number. 100 million. Now, that's how many parameters a pretty standard AI might need. And get this, that's just for its embedding layer. You know, the part of the model that's just trying to figure out what words mean in the first place. It's this massive, incredibly expensive foundation before the AI even starts doing anything else.
I mean, this explosion in size has led to some incredible breakthroughs for sure, but it also forces us to ask a really important question. Is this brute force approach, just making models bigger and bigger and bigger, is that the only way to move forward? Or is there a smarter, maybe more elegant way to get the job done? So here's how we're going to break it all down in this explainer. First, we'll tackle the scaling problem. Then, we'll get into the quantum-inspired solution. We'll look at the actual math that makes it all possible, weigh the promise against the real-world challenges, and then wrap up by thinking about what this all means for the future of AI itself.
Okay, so first up, the AI scaling problem. You see, the way we teach AI language right now is by giving each word a location in a space, but a space with thousands of dimensions. And as it turns out, having more dimensions can actually create a whole lot more problems.
The main problem is something that mathematicians call the curse of dimensionality. Just imagine a space that is so vast with so many different directions that every single point starts to seem equally far away from every other point. Now, for an AI that's trying to figure out if the word king is closer in meaning to queen or to cabbage, this is a huge issue. All those meaningful connections just get lost in the static.
And you can see the difference here. It's just night and day. On the one hand, you have the old way, thousands of dimensions, huge costs for storage and computing, and that curse we just talked about. And on the other hand, you have the goal of this new quantum approach, cramming all that meaning into just 2 dimensions, making it super efficient and completely avoiding the curse. So the billion-dollar question is, how on earth is that even possible?
Well, that brings us right to our second section, taking a quantum leap for language. Now, to be clear, we're not talking about building a full-on quantum computer to run a language model. Not yet, anyway. This is all about borrowing a few of the superpowers from quantum mechanics to help us solve a very classic problem with data.
The first superpower on our list is superposition. It's a foundational idea in the quantum world. A particle isn't just here or there. It can actually be in a combination of many different states all at the same time.
So how does that help us with words? Well, think about a word like bank. A classic AI has to kind of guess which meaning is right. But using superposition, you can have the word bank exist as both the side of a river and a financial institution at the same time. The other words in the sentence would then help the AI figure out which meaning to focus on. It's just a much smarter way to handle words with multiple meanings.
Okay, the second quantum superpower is entanglement. This is the one Einstein famously called spooky action at a distance. It's a wild idea. When 2 particles are entangled, they're linked. If you measure one, you instantly know the state of the other one, even if it's light years away.
So for language, this is like having a pair of magic twins inside a sentence. An AI could use entanglement to link a word like it at the end of a really long paragraph directly back to the specific thing it was talking about way at the beginning. This could be an absolute game changer for understanding complex stories, something current AIs really struggle with.
Okay, so we've got these incredible quantum ideas. Superposition, entanglement, great. But how do we actually go from thousands of dimensions all the way down to just 2 without losing all the important information? Well, that brings us to the really elegant math behind this big squeeze.
The whole process is called eigenvector mapping. And you know, the concept is actually pretty clever. First, you start with your huge 1,000-dimensional data. Then, you build a matrix to see how all the data points relate to each other. From there, you use this mathematical tool, eigenvectors, to find the most important patterns, the directions where the most meaningful information is. And finally, you take those key patterns and you map them onto a simple 2-dimensional plane.
But wait, how do you squeeze all of that information down and not lose everything important? Well, that's the magic, right? First, the eigenvectors. Make sure you're only keeping the most important stuff. But the real genius here is that you're not mapping it to a simple 2D grid. You're mapping it to a complex plane. This means every single point has both a distance from the center, its magnitude, and an angle, its phase. You can use one to encode how strong a meaning is, and the other to encode what category it belongs to.
It's a trick that basically doubles the amount of information you can store in that tiny 2D space.
All right, now for the reality check. Like with any amazing new idea, there's always a gap between the incredible promise and the practical, real-world challenges. So, let's talk about the potential versus the reality.
The promise here is just huge. I mean, think about it. Machine translation that's way faster and more efficient. Search engines that give you better results instantly. You could even get more creative AI that could write nuanced poetry. But maybe the most exciting thing is the idea of running really powerful, sophisticated AI models right on your phone without needing to be connected to some giant server farm.
But, and this is a big but, we have to be realistic. To really use these quantum effects, you need quantum hardware, and that stuff is still very, very early. It's noisy and prone to errors. And going from a small proof of concept to a system that can handle millions of words, that's a massive hurdle. We can fake it on today's computers for now, but that's just a temporary fix. It's not the final hyper-efficient solution we're all hoping for.
So, where does this all leave us? As we get to our conclusion, it's pretty clear that this is about way more than just a neat efficiency trick. This could be a fundamental shift in how we think about, well, how AI thinks.
And the author of the source material, L.F. Yada, really nails it with his quote. This isn't just some small technical adjustment. It's a fundamental rethinking of how we represent and process information. The way an AI sees the world is completely defined by how it represents data. If you change that, you could change everything.
And that really leaves us with this one big, fascinating question to think about. The AI models we have today, they think in thousands of dimensions. If we can teach them to think in a two-dimensional quantum space instead, using these wild ideas like superposition and entanglement, are we just making them more efficient? Or are we actually fundamentally changing the nature of their intelligence? Thank you for watching The Explainer.